Hello and welcome everybody to this fifth lecture on inverse problems in medical imaging. Before we start with the topic of today, I'd like to very shortly recap with what we ended last week. We discussed least squares and we derived the least square solution of a straight line. We said that usually we use least squares when we have sort of more observations than unknowns, and we figured out that the solution to the least squares problem can be calculated using the formula I've written down here. Then we did another method or inverse method based on length, and it was the minimum length solution. And what we did or what we said there is we add some a priori information or whatever constraint that comes to our mind. And if you remember during the derivation of the minimum length solution, we said that the constraint we're gonna add is really minimum length and therefore the name of it. And through some calculations and some fun stuff we did there, we figured out that the solution or the minimum length solution here is given using the formula here. For both cases, we said, of course, they are only calculable this way and they only exist if the inverses exist. There are cases where the inverses not exist. And we have still this case a bit open in our mind. What if we cannot do least squares? What if we cannot do minimum length? And what should we really do? And we start to answer this question, this general, what should we do today? So we have generally two topics for today. We start with weighted measures of length. So we add a weight to everything we did. And then secondly, we start with the generalized inverse operator. This is actually my favorite operator of this class here because it is the solution to everything. We do not finish with this topic today, but we're just gonna start with it. As I said, we're gonna start with weighted least squares. We should discuss shortly what this means in comparison to the thing we're doing at the moment. So if you remember at the moment when we were talking about least squares, we were minimizing the thing I've written down here. So we had the error term for each observation we have included in our problem, and then we minimized this cost function E. And we changed something now, and we changed this error function E. So what we assume is a new error function. It is written down as E transposed omega E times E. So compared to the thing we had previously, we have this weight matrix included herein. So it's an n by n, so a diagonal weighting matrix. We're gonna see in a second what it can be and what it does. So what we often use is the inverse covariance matrix. Probably I should very shortly recap what the covariance matrix is for you. Let me write it down here. So the covariance matrix of X is defined as the variance of the first property, then the covariance of the first and the second, and so on until we reach the last. So we have the covariance of the first and the nth property. And of course, we do the same here for the columns. So we end up here with the covariance of xn, x1, and so on until we reach the diagonal where we have the variance of xn. And so here we say we use the inverse covariance matrix for weighting. Of course, the first question that comes to our mind here is why are we doing that, or what does it do to our problem? So what we can see immediately, or what we recognize immediately, is data with a large variance are weighted less than the ones with a small variance. So this means data that fits to the solution already kind of good will be weighted more then data that is a bit off. If you think about, for example, a polynomial or whatever, and you add some noise, then of course you wanna get rid of the noise. But with noise, you get a large variance. And when we use now the inverse covariance matrix for the weighting, that we might get rid at least a bit of the noise. So this is really the reason why we do that. There's one special case, and it's actually the special case we're going to discuss next because it's so easy. We assume that the covariance matrix now is completely a diagonal matrix. Diagonal matrix means that the data are uncorrelated. So data point xi, for example, has nothing to do with data point xj. And therefore, this matrix, this weighting matrix we just built, we called it omega E, is a diagonal matrix. And of course, you know already that you can very easily invert the diagonal matrix. I just did it here for you. And this is what we use now for the next couple of slides. So when we use this new weighting matrix E and we calculate the total misfit, we end up with this nice formula here. So we can write this sort of scalar product E transposed omega E times E using sums. And since, as we said, omega E is a diagonal matrix, we're gonna end up very easily. In here, I think we discussed it already, but let's just shortly recap it. This delta ij stuff here is called the Kronecker delta, and it is 1 if I is equal to j, and it is 0 else. And the reason why we have it here is because we say the data is uncorrelated, therefore we have nothing on the off-diagonal elements of the covariance matrix or the inverse, and so those things are just multiplied with 0. So we have here now the total misfit given. Of course, the question is, what are we gonna do with it? And first big thing for today is we obtained a weighted least square solution. So compared to the previously defined least square solution, the only thing changes is that we're gonna add the covariance matrix like we just did, and we assume that it's diagonal. So this is sort of an assumption we are doing here. So the next couple of steps we only gonna do for a diagonal weighting matrix E. We have again our usual problem, D equals G times N, which should be the problem of the best fitting line. Okay, then let's start. We have 4 steps ahead of us. So step number 1, we look at the total misfit a bit more closely. We know already that it's now defined as E transposed omega E times E. And since it's a diagonal matrix, we can write this thing here down as the sum over the omega I times EI squared. Now, if you remember, one of those simple EIs contains sort of the difference between the observed data point and the original data point. So we're gonna plug that in. Now, once again, same thing we did already a couple of weeks ago. We get rid of this observed here in the notation. And for the predicted DI, we're gonna plug in the straight line. So in here, I've just written down sort of a matrix vector notation of a straight line. We said that the problem we had originally is given as D equals T times M. But of course, T is an n by 2 matrix since we have a straight line. And you see in a second what it transforms to. So if I'm doing some recalculation, we still have the omega I in front. But in here, we have on the one hand the di squared that were originally the di observed. But then we have everything regarding our straight line. So nothing really has changed compared to the thing you know already. The difference is really only in front here, where we have the omega I included as weighting parameters in front of the derivation. So step 2. What are we doing when we would like to minimize a function? Question to the audience.
We derivate.
Exactly. So same thing we did 2 or 3 weeks ago. So first with respect to the parameter m1, but I'm not doing the whole derivation with you. I will sort of just tell you what the result is and you can watch by yourself if it's true. I get rid of the i's in the sum here. You know that the sum goes from 1 to n. So we have dii omega ii on the one hand. Then we have 2 times m1, the sum over the omega ii. And we have 2m2 sum over the zi omega ii. And this thing here should be 0. Okay, number 2. Same thing with m2. So we have the sum over the di zi omega ii. Then we have 2 times m1. And we have 2m2 times zi squared. Again, this thing here should be 0. Now, after we have finished this lecture, when you look back to the thing we did 2 weeks ago for general least squares without a weighting parameter, you will notice that this step in the derivation looked exactly the same. The only difference is here that in each term, you have the weighting parameter included. So we can write down a matrix form. And we have the sum over the omega i's. Then here, the sum over the zi omega I. Same thing. And here we have them squared. And once again, what you will figure out compared to the last time, we have only the omega i's here in addition, but everything else remained unchanged. Okay, and on the right-hand side, we have now the sum over the di omega ii. And here zi di omega ii. Okay, I'd like to copy that to the next page so that you can see it. Let's continue with step number 3. When we look at the left-hand side of this problem we have written down here, we see that the matrix, please note that it's a 2 by 2 matrix again. can be rewritten once again. And now we use G transpose omega E times G. And once again, the only difference compared to the last time is this matrix omega E here in the middle. So for the right-hand side, we have that the sum di omega ii, and then with the z is nothing else than G transposed omega E d. And once again, only difference is this matrix omega E here in between. So those two things, I've just written it down without the derivation, but I'd like you to prove them yourself. If it's really true what I just told you. Okay, and then step number 4, last thing missing in the thing we just did. We look now at the problem G transposed omega E GM equals the right-hand side G transposed omega E D. So that again are our normal equations. And now, of course, the usual thing, the weighted least square solution can be now written as the inverse of this matrix on the one-hand side, and then the right-hand side. But of course, only if the inverse exists. There's one thing here I'd like you to note. I did the derivation here only for a diagonal matrix omega E. It is true when we consider a full covariance matrix as well. And the derivation would be very similar, but way more lengthy. And therefore, I decided on doing it with a diagonal matrix here so that you really can see where everything plays a role and how everything goes into. Okay, we just discussed weighted least squares. The obvious next thing we're gonna do are weighted minimum length. So we're gonna do this here without purely the derivation. We have seen already in the least squares case how it works, but we rather discuss where things will change. So first, when we have minimum length, we said we want to minimize the parameters. So what we do, we now minimize M transposed, omega M and M, where omega M is once again the inverse covariance matrix. Please note that we had the inverse covariance matrix just before with the least squares, and there we called it omega E. So on the first glance, it doesn't really make sense. But I'd like to have another notation here because in the end, we're gonna get those two things together and then we see a bit of a difference from where things come from. So in the last week, we said we do not only can do minimum length, but we can say that the estimated solution should be as close as possible to some desired or expected solution or whatever. So what we're going to do is we replace M with M minus this funny looking M, where it is the expected solution. Or estimate. So before we had the total misfit E, and we included the weighting matrix. And we do some sort of the same here. So we define an operator L that is given as, on the one hand, M minus the expected M transposed, omega M, and then once again, M minus the expected one. So compared to previously, where we had here just M transposed, omega M, and then M, we have here M minus the expected. And of course, what the goal is to minimize L. So as I said, we do this without derivation today. I'm pretty sure you will believe me what the final solution is. And we find out that the weighted minimum length solution is given as the expected M. And then we have the inverse of the weighting matrix, G transposed. Then this parameter or matrix we know already. And then here D minus G and the expected M. And therefore, sort of the weighted minimum length operator is given as omega M inverse, G transposed, and then this thing here. And of course, only if the inverse exists. So we included now a weighting matrix, a weighting factor to the least squares and to the minimum length, but we did not combine those two so far. And this is what we're gonna do next. When we discuss the weighted damped least square solution. So what you should note, we have those covariance matrices here in the example, but in general, you can put in here whatever weighting matrix you want to have. But if one of those are nearly singular, then we have instabilities. And I always said we can only do this thing if the inverse exists. So there's always this question left. What are we going to do when the inverse does not exist? And a sort of an answer will be given here by using the weighted damped least squares. So we changed the cost function. Previously, we had either weighted least squares, where we had the usual operator, or we had the weighted minimum length, where we wanted to minimize M transpose times M, or whatever weight we have in there. And now we combine those two. So we say we have a new functional. On the one hand, it consists of the weighted least squares, and on the other hand, it consists of the weighted minimum length. And this epsilon square here is at the moment just a weighting parameter. You will see in a second what it does more closely. I will just once again write down what the solution looks in this case, but you're going to see where least squares and where minimum length play a role. So we define the solution as M omega D, so weighted damped, and then least squares and so on, we can get rid of that. So on the one hand, we start with the expected M, and then we combine least squares and minimum length. So we here have sort of the least squares operator. And now we add the weight of the minimum length operator with parameter epsilon. This is one possibility. Or here's the second possibility. We still start with the expected M, but then we start with the weighting factor weighting matrix of the minimum length. And then we have the usual stuff here. And my apologies, the inverse here should be, of course, outside. So let's discuss for a second, what are the important things therein? It's the things where we have the inverse. Now we figured out two possibilities. On the one hand, the focus is a bit more on the least squares. It is in the first possibility where we really would like to solve the least squares. And with this parameter epsilon, we try to shift stuff a bit so that this thing here might get invertible. In the second case, we have to focus more on minimum length. And the weighting matrix of the least squares is just included a bit once again with a weighting parameter. Now, I would just like to tell you in words what to think about. I do not expect you to fully understand it or to know it for the exam, because we do not do that. First of all, what is the issue or what is the main reason why we cannot invert a matrix? And we think about a square matrix, then it's that the eigenvalues are zero. So we do not like zero eigenvalues because they leave us without an exact or unique solution. What we can do when we add, for example, a diagonal matrix to the original is we can shift the eigenvalues away. So we might shift the eigenvalues away from those zero eigenvalues where it gets invertible. And this is exactly the thing we try to do with those two things I've written down for you. We try to shift possible non-zero eigenvalues away from zero to get them invertible. There's one further thing I'd like to say here. In a couple of lectures, we will start with regularization. I am pretty sure some of you know regularization already a little bit or work with it. And we find out that things there look actually quite the same. And what we will see is regularization is more like a broader topic than the thing we did here. So regularization can really try to make your problem solvable. So as I said, this is some sort of explanation which you do not need to fully understand, but that's a bit to the background why we are doing the things here. As I said, and just to write it down, there's two important matrices, sorry. On the one hand, it's the one that focuses a bit more on the least squares, the way we have written it down. And then, of course, we have G transpose omega E back there if we want to include it. And on the other hand, and you should notice that I used the same parameter. It is the second matrix. And it can be shown that those two are equivalent. So this means you do not have to decide on where to put the focus on. When they are equivalent, it doesn't really matter if you add the parameter to the or parameter times weighting matrix to the least squares or to the minimum length. And last thing here to note, this epsilon square has an effect, or it is sort of the effect of damping the instability. So once again, instability means that we have zero eigenvalues or zero singular values, and we just try to shift them away from the zeros to give us a possible solution, or so that this problem is solvable at all. Now, I guess this was a bit of a hard part. Let's go to something fun once again. I'd like to discuss adding a priori information or constraints. When we discussed the minimum length solution last lecture and this lecture, we focused on minimum length as a priori solution. But of course, we can include different constraints, so different previous knowledge we wanna add because we're just sure of it. And there's two approaches I'd like to show you today. And we just start with the first one. So we want to add the linear equality constraint Fm equal to h shift. Just written it down here. So the idea is to include the matrix F that models the constraint in our forward problem. Step number one. We want to include Fm equal to h to our original problem. So we end up in Gf and then the model vector being equal to d and h. So G times M equal to D was our original problem, and the constraint problem is now F times M equals H. Okay, step number two. We want to build this misfit vector E. And since we're doing weighted measures of lengths already, sorry, that will follow in a second. We're still here with our usual misfit on the one hand, so observed minus predicted. And on the other hand, we have here the constraint. But that was what I wanted to talk about a second ago. We are already in the area of weighted misfits. And what we do now is we discuss a special choice of the weighting matrix. So we assume it to be a diagonal matrix, and then it should have ones in the first place. And then I just call them big. We discuss in a second what that means for the second. So here we should have P of those big values within the constraint, and they correspond to H. And those ones, they correspond to the original matrix D. So this means when we have our problem Gm equal to D, we do not change it. So we leave the problem as it is. But we really weight the additional constraint. So we sort of give the problem the information that the constraint has to be fulfilled no matter what. So constraint is like priority number one. And then the original problem, Gm equals D, this is priority number two. And once again, in a week when we discuss a bit regularization, you will figure out that this might look a bit similar. So when we said there is a first approach of including constraints, then of course there's a second approach of including constraints. And this is with using Lagrangian multipliers. Okay, step one. We build some funny function phi. We have our usual misfit, and then we add the constraint as fm minus h, and we multiply it with some lambda. And we can calculate it as the sum over I of di. So nothing really has changed here. You know the stuff already. But here we have left the constraint lambda I, and then we model the constraint therein. Step number 2. What are we doing? Of course, we build the derivative. So when we do that, once again, and without the full derivation, I'm pretty sure you're going to believe me. Now it's time for matrix vector multiplication once again. And step number 4, we need to build the inverse. And there we're done.